Hi, in this presentation, I'm going to talk about predicting the heating of rotor in a PMSM. PMSM stands for Permanent Magnet Synchronous Motor. It is a component used for electric-driven cars or electric lifts. I will talk in two parts. The first part of the presentation will introduce the project background, the data set, and the some background information and introduction about this project. The data set I obtained is one from Paderborn University Laboratory, published in Kaggle in June 2019. It is a set of measurements recorded from experiments done on the PMSM and comprises data taken from sensors attached to the PMSM on a test setup, test bench, while it is driven through a number of driving cycles, simulating perhaps driving patterns in the real world. The features that will be found in the dataset talks about things like currents in the DQ coordinates and voltages in the DQ coordinates. And these are frames of references adopted in the so-called motor analysis or electric motor analysis in electrical engineering. From the data sets, one can gather that the possible target features are rotor temperature, stator temperature, and torque. The rotor is simply the rotating part of the motor, and the stator is the stationary or the frame part of the motor that is inside the motor housing or the frame. So, the use case that I have chosen is to predict rotor temperature, because this has a benefit that the industry can choose suitable material for the magnetic material for the rotor surface. And additionally, I will try to predict clusters from the measurements to determine if there are patterns or operation states which could be further investigated with domain experts. First, the data set. Well, as you can see, the data set consists of something like 13 columns, and I won't talk through what you can see on the slide about the meaning of each of those columns. It is from these columns that we would select some features for our modeling later. The solution to the use case is described in a Jupyter notebook, which shows and records the project execution in step with the work process model recommended by IBM. In the result, you will see that we will use two models, a linear regression with elastic net and a gradient boosted tree model to do the prediction of the rotor temperature. And with these models, the performance on metric of R2 are respectively 0.635 and 0.483. In the k-means clustering modeling, we found something like 15 clusters in the measurement. I move on next to part 2 of my presentation, where I would give more supplementary information that describes in further details the project execution. The topics covered in this part comprise technology choices, data exploration and data quality assessment, data pre-processing, feature engineering, model selection and training, model performance, and then some closing remarks on the further development recommendations or further explorations. I tabulate here the technology choices in line with the architectural documents recommended by IBM, where in the components of data source, enterprise data, streaming analytics, data integration, data repository, discovery and exploration, I documented the choices made and the reasons for those choices. Uh, Essentially, the key thing to note is that for data source, I derive my set from Kaggle through the internet. The reason being wide choices are available and it's open source. And it's also very popular. Enterprise data, streaming analytics, well, basically it's Paderborn University proprietary enterprise data source they have, but I think they loaded this set of batch data for us on Kaggle. So we will need streaming analytics here. On data integration, repository, discovery exploration, a great help is fundamentally from IBM Cloud and IBM Watson Studio. The access is well managed and secure by IBM. On the cloud storage front, the price is tiered to use and transparent, therefore secure and reliable with backup worldwide in a number of regional centers. Very essential to the work at hand that I did was the use of IBM Watson Studio Jupyter notebooks, scikit-learn, pandas, matplotlib, MPL toolkits, Python, and Apache Spark SQL. Essentially, the IBM Watson Studio is an integrated project development tool, and so with notebook, machine learning frameworks, visualizing, and data repository in one, working seamlessly, and projects can run on environments which one can choose. Well, just some comments about data exploration and data quality assessment. The CSV file has data from 52 measurement sessions. Each row represents one snapshot of sensor data at a certain time t. Inside each measurement session. And the sample rate is 2 Hz, meaning that one row every half second. So what happens now is that one can calculate that each independent session is identified with a profile ID, and it lasts from 20 minutes, in which case you gather something like 2,400 measurements, to 6 hours. Then you talk about 2.2 million or so. In this instance, the batch data consists of a measurement population of close to 1,998,070 rows of measurements. There are 13 columns, a profile ID, which is string formatted, and 12 feature columns, which are from sensor data, and therefore they are floating point data. Well, the encouraging part of it is the data usability rated by Kaggle is 10. It makes for confidence to use the data. But in any case, as part of exploration, we check it for null values, duplicates, and interest. And very helpfully, the data has been scaled already by the Paderborn University team. I did the data visualization with matplotlib, MPL tools in Python environment, and pandas data frame. Being more experienced in that area. For the data pre-processing and feature engineering, I had to instantiate the Spark environment because of the scale up data, and converted firstly the pandas data frame to Spark data frame. And I created a feature power being the output of a PMSM, actually is horsepower, and is heat related. Therefore, a possible predictor for motor or rotor temperature. Power is essentially the product of torque and the motor speed, and in consequence, we reduce the two correlated features of torque and motor by 1. Model selection and training, the PM prediction basically is a supervised learning problem because the target feature is a continuous variable, and so linear regression is selected. To get another opinion or a cross-check, perhaps even possible improvement, the gradient boosted tree is selected as a second model. The training and test sample split is a change from the default of 0.8 to 0.2 to 0.9 to 0.1, and I tuned the learning rate to 0.1 from 0.3 and the elastic net rag parameter to 0.9 from 0.8, giving it a little bit more lasso effect, and for the linear regression model. And the training took more resources and longer with GPT or gradient boosted tree than linear regression. And voila, here's the results that I managed to achieve with the linear regression model on R2 metric 0.635 and on RMSE is 0.603. In the Jupyter notebook, there will be a little bit of more detailed comments regarding the standard deviation and how this RMSE compared with the standard deviation. For the gradient boosted tree, the RMSE is slightly more accurate at 0.483, and whilst the R2 seems to come down somewhat to 0.483. Nevertheless, trying to figure out the adequacy of R2 is something which needs to talk to also the client's acceptability criteria. And as long as it's pretty much in the range of 0.5 and 0.6, it's pretty good. But as one knows that high R2 on its own merit doesn't really say much without further understanding of the data. And for example, plotting residues plot would be helpful. Well, one next I did was that I used Spark ML K-means as a clustering model to cluster the measurements and to see if there's some patterns of operation that could be reviewed. And firstly, the elbow method is used to find the optimal cluster number, and turns out to be 15 in my case, in my work. And when I then try to determine the size of the cluster, I run into a bit of difficulty with the Spark data frame, how to do this, and I converted then the Spark data frame to a pandas data frame where I could count the values in each cluster. And then I managed to find that cluster 5 is the one with the largest population and could perhaps merit further study with the domain experts, the implications from there on. So some further work to do. Thank you very much. This ends this part of my presentation on reporting back the findings.